Got it? All right. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you again, Lord, for these students. I just pray that you just help us today to understand the material. Again, Lord, we thank you for your grace and mercy to us each and every day. Lord, we thank you that you died on the cross for our sins, and if we just accept you into our heart, we have your forgiveness, that your righteousness is our righteousness and not our own, Lord, and we thank you for that. I just pray again that you help us to understand these topics of differential equations, and you just continue to encourage the students as they work on this course, Lord. In your name I pray. Amen. Okay, so let me start in the separation of variables. So we're in section 9.2, separation of variables. So I'm gonna try to follow the book here for a little bit, but then I will pretty much divorce myself from the book in terms of how we actually calculate things in here. I will show you how I learned to calculate these things and how you should calculate these things, because it's a stupidly simple way of thinking about it. So we assume we have two functions, I think big P and big Q. And have P prime equal to little p, and I'll give the big P a foot there, I can tell. And Q prime equal to little q, and we're assuming that the little p and the little q are continuous. That is, that we're supposing the original functions, big P and big Q, are what are called continuously differentiable functions. They not only have derivatives, but their derivatives themselves are continuous functions. All right, well, then Jonathan Hilly tells us to look and say, okay, well, if you have some equation like this, P of x plus Q of y equals to a constant, well, that's an interesting kind of curve to look at. Usually we call these things graphs. I mean, it's really the solution set, the set of x and y that solves such a thing. That's a graph, right? Now, that's a special kind of graph, though, because I'm assuming it can be written in this form, and certainly not all graphs can be written in that form. But then we do a little bit more. Then we suppose that y can be written as a function of x. So in other words, assume you can write y as function of x. Now, if that's the case, then we can differentiate implicitly. Right? This is just what we do in Calc 1. So we're going to take d dx of big P of x, right, plus d dx of q of y of x is equal to d dx. Now, I'm using the linearity of the derivative, right? Sorry, derivative of a constant, but I might as well put a 0 there. This is what? 0, right? The derivative of the constant term is 0. Now, the derivative of p is just little p, right? So, but I'll just do one more step here. This is p prime of x plus q prime of y of x times what? Times dy dx. So make sure that so there's like none of the paint should be showing in the video, right? Okay. So that's equal to 0 by the chain rule, right? So you can rewrite that in terms of the little p and the little q, and what do you get? We get p of x plus little q of y of x times dy dx is equal to 0. And then he says, okay, so that's a differential equation, right? I mean, okay. let me go one step different than the book. So we have p of x is equal to minus the integral of q of y of x dy dx, right? Sorry, there's no integral yet. But then my point is, you could, okay, well then we could do what? We could integrate both sides with respect to x, right? We could compare the indefinite integral of p to the indefinite integral of q of y of x dy dx, and what would that give you? I mean, the left-hand side is what it is. But the right-hand side, we could look at that in terms of a what substitution? We could really look at this as what? Like we're making the x's cancel, right? And you're just left with dy. I mean, that's u substitution, right? So by the change of variables theorem for integration, this is really just minus q. Oops, sorry, minus outside. Put the minus outside the integral. So this is minus the integral of q of y dy. So in other words, if a differential equation has this format, all right, if the differential equation looks like this, right, then it permits this as a solution. But let me show you some, this. Let me just redo. Same argument in the so-called differential notation. The notion of a differential is very old, and it's somewhat fallen out of favor in modern calculus teaching, but that's unfortunate because it's very useful. So my point would be, we could instead look at the boxed equation as maybe you're given dy dx is equal to, I don't know, minus p over y, minus p over q, right? So this is, this is given. It's almost the same as what I have over here, right? Except that, something would be lost, right? If there was some possibility that q of y was 0, we'd lose track of that when we made this division, right? So to be really careful, I would say they're not quite the same differential equation, because you might have lost like q of y equal to 0 kind of stuff. But ignoring that rather exceptional case, it's the same thing. So then what you do is you put everything with y on one side and put everything with x on the other. So I get like q dy is equal to minus p dx. I'm omitting the x and y dependence. You integrate both sides. And okay, so I mean, fine, I put the minus on the other side, but I think you see, same thing. So all I'm trying to tell you guys is this. This somewhat careful argument, right? This argument that's based on the chain rule and then ultimately the application of the u substitution theorem for integration is entirely equivalent to the symbol pushing over here, this formal nonsense that you can just separate variables at the level of differential notation and integrate both sides. That's very nice because that is super, super easy to remember, whereas this, while being more correct, is not as easy to implement. Okay, so examples. How about this? dy dx is equal to minus y over x. Oops, sorry, x over y. There is still a giant gaping hole in this whole discussion over here, this assume business, you know. How do you know you can write y as a function of x locally? Like, what's that about? How do you study that carefully? How do you know you can do that for an arbitrary equation? Actually, you can't. What's needed there is the so-called implicit function theorem, which we actually talk about in the advanced calculus course. Math 332 here. All right, so what I do then is I follow my generic advice, separate variables at the differential level. So this gives me y dy is equal to minus x dx. And then I integrate both sides. All right? This gives me 1/2 y squared is equal to minus 1/2 x squared plus a constant. And then I solve. I get x squared. I mean, I'm solving for my own reasons. I think you'll see why. This is the so-called implicit general solution. The implicit general solution. What are those for different values of c? Come on, guys, what are these? Circle. How about what if c is equal to minus 1? Yeah, it's right. It's not possible to take the sum of squares of two real numbers and get back minus 2. No can do. If I put c equals to 0, it's a very silly circle. Or maybe it's not a circle at all. I guess it depends on your definition. I would say it's a degenerate circle. I don't know. It's the origin, right? That's there. But setting that aside, you've got concentric circles, right? Different values of c give you different circles, right? And you can see that what happens is that as you allow the values of c to go over all possible real numbers, you're going to get every point in the plane covered. In fact, every point in the plane is covered by just one of these solutions, right? So if you pick a point in the plane, there's going to be a unique circle that goes through it that's a solution to this differential equation. Now, how about this business? Assume you can write y as a function of x. How does that, let me just talk about that for a second here. So, like, in particular, the top, right? This piece right here I can solve with what? This would be y is equal to, solve this, 2c minus x squared, right? That gets that part of the solution. How about the other part? This down here is y is equal to minus the square root of 2c minus x squared, right? This particular boxed equation we can solve, right? We can solve for y without too much trouble there, really, right? Now, there's only one point, well, 2 points really on this circle where I cannot solve for y as a function of x everywhere close to the point. What are those 2 points? See this point right here and this point right here I can't solve for y as a function of x, right? Because if I had a solution there, it would have to follow the circle close to it, right? And as you can see, if you follow the circle close to those 2 points, you know, well, let me not get into the details of what those points are, but you can see they're going to fail the vertical line test, right? Those are not functions, right, of x. What's the significance of that if you look back at the differential equation? Well, check this out, right? Y equals 0. Also, y equals 0. Those 2 points, actually, are where this differential equation breaks down. In contrast, I suppose, that is one advantage, right, of this thing, p of x. I mean, if you rewrite this, if I really embrace the differential notation, I would write this. I would say p of x dx plus q of y dy equals to 0. That would be, this is a more fair-minded presentation of the differential equation. The distinction between what I just boxed and what I wrote over here is that this puts x and y on an equal footing. It makes no distinction, really, at the level of algebra, the distinction between y and x. Of course, there is obviously a distinction between y and x made in this formulation because we're talking about y being a function of x. Whereas if you think about that sort of thing, it's more open-minded. We wouldn't lose these points if we used this as our way of thinking, because it makes no distinction between up and down and left and right formulaically. I'm digressing a little bit now. So let me get back to track. So here's our implicit general solution defined. These are explicit solutions, but they're only local. They don't cover the whole circle, right? So I don't even want to try to write the explicit general solution here because I'd have to use case-wise to find things. I'd have to have 2 cases, one for positive, one for negative. Any questions? What if I want to find, let me just tweak this a little bit. What if I want to find a solution to this differential equation which goes through a specific point? Suppose I want to find the solution that goes through this point, like say x naught, y naught. Let me show you a way we can do that. So just a simple twist on what we just did. If I want to build a data point into the differential equation, I start in the same place, and so I'm trying to solve dy dx equals to minus x over y with y of x naught equals to y naught, all right? AKA x naught, y naught on the solution curve. So your textbook calls these integral curves of the differential equation, which is a pretty good term for it, right? You get it from integrating the differential equation. These are also known as level curves because, well, more on that. Or sometimes they're called contours. Now, so kind of the same song and dance, but how about this? I say dy times y is equal to minus x dx, right? And then what I do is I integrate this one from y naught to y1, and I integrate this one from x naught to x1. Remember, this is just a notation for u substitution. So what do we do when we do u substitution? We change the bounds, right? So what's assumed in this is that like y1 of x1 is equal to, well, y of x1 rather is equal to y1, right? And y of x naught is equal to y naught. I mean, that's what's the idea here. And the reason that that's valid is the u substitution theorem, change of variables theorem. Now you can integrate, right? This is 1/2 y squared evaluated from y naught to y1 is equal to minus 1/2 x squared evaluated from x naught to x1, which gives us 1/2 y1 squared minus y naught squared is equal to minus 1/2 x1 squared minus x naught squared. But I can solve that for x1 squared plus y1 squared. And what do I get? x1 squared plus y1 squared is equal to x naught squared plus y naught squared. Yes, sir.
Squared above the x not supposed to be inside the parentheses.
Yes. Thank you. See, but this x1 and y1, it's just an arbitrary point on the solution, right? So we might as well just call it x and y to unclutter this and to capture the general solution, right? So we just say, okay, so set x1 equal to x and set y1 equal to y. And that gives us x squared plus y squared is equal to x naught squared plus y naught squared. And that, of course, is the solution to that differential equation, which goes through the point x naught, y naught. So you can build the data point into the solution by integrating like this, if you want to. What's the other way you could do it? Not terribly complicated. You just go back to this thing, right? And just suppose x naught squared plus y naught squared is a solution. That means x naught squared plus y squared is equal to what, 2c? So then you take the 2c and you replace it with that. I mean, so you can either just calculate with an indefinite integral and then plug the data point in at the end, or you can build it in with integration. It's up to you. Yep. Oh, yeah. I'm sorry. I think I thought that was supposed to be a comma originally, and then I added a second comma, thus confusing. There. Yes, that's just supposed to be x, right? This idea about using bounds which are variable in this sense is yes, sir?
What's that word right there? Does that say aha?
Oh, no, that's aha. No, that's no, I am known to write aha here and there, but that is in fact an AKA. Aka! Let's see here. Sorry, this is now a silly place. Let's see here. For the rest of this lecture, you may refer to me as throat wobbler mangrove. Let's see here. So, example. You guys don't know about the throat wobbler mangrove? No? Probably a Scotsman. Sorry, it's wrong to insult people with fictional genres they're not familiar with. It's not nice. Sorry. All of a sudden, it's got ugly. I'm gonna stop digging this hole. All right. Let's see here. There's an example in your homework which is kind of physicsy. I want to talk about that for a little bit. So we could talk about a force of friction, which was something like beta v cubed, or say I think a minus beta v cubed, where v is the velocity. And you could ask questions like, okay, so if the force of friction is this for a particle with mass m, what's the velocity as a function of position? What's the velocity as a function of time? Okay. Find v of t and v of x, where particle. How do you spell particle? I don't remember. Particle, yeah. That seems wrong. I've forgotten how to spell particle. What's wrong with me? Let's see here. Particle has mass m. Now has two s's on it. Good gracious, what is wrong with me? Mass m. So here, v of t, of course, is dx dt, right? And the a is acceleration. It's dv dt. All right, so I'll start by finding velocity as a function of time. So Newton's second law, which we know, is ma is equal to minus beta v cubed. If you don't know it, well, there you go. Learn. That's Newton's second law. All right, so mass times acceleration is equal to the net force applied. And so what we have here is we've got m dv dt is equal to minus beta v cubed. Well, that's a differential equation. In fact, that's a separable differential equation. So what I can do is I can put all the v's on one side and all the t's on the other side, and that will get me a dv over v cubed is equal to minus beta over m dt. What have I done? I hear there's something amiss. No? Okay. What's that? Now integrate both sides, right? What do we get? We get minus 1 over 2 v squared is equal to minus beta t over m plus some constant. Now that's an implicit general solution for the velocity as a function of time, but I can solve this for v. Like this gives me 2v squared is equal to 1 over beta t over m minus c. Then I can divide both sides by 2, and I get v is equal to plus or minus 1 over the square root of 2 beta t over m minus 2c. There you go. That's the velocity as a function of time. It ain't pretty, but there it is. Now, in contrast, right, I could look for the velocity as a function of position. To find v equals to v of x, we need a trick. What was the question? No. So acceleration, right, is dv dt, which is dx dt times dv dx. Now, that is assuming that we can rewrite the velocity as a function of x. It's probably only going to be reasonable for one-dimensional cases, right? And even so, it's an abusive notation. The v on the left-hand side is a function of t. The v on the right-hand side is a function of x. But I'm using the same symbol v for both functions. But this is a common abuse. So since everybody else is doing it, it's okay, right? So this is v dv dx, which is very nice. See, that's v, right? So we find that what we're really facing here, on the other hand, we have ma is actually equal to m v dv dx, which is minus beta v cubed, continuing my example, right? And so to find the velocity as a function of position, I face a slightly different problem. So I separate variables, right? What do I get? This time I get dv over v squared is equal to minus beta dx over m. Now, of course, I can do the same song and dance over here. I can just integrate both sides, add a constant. But you know what? I'll do a little bit more for you this time. I will relate the final velocity to the initial velocity and the final position to the initial position. The way you do that is just integrate this, say, from v naught to vf, and integrate that over the corresponding x naught to xf. And when you do that, you'll get this. Minus 1 over vf minus plus 1 over v naught is equal to minus beta over m xf minus x naught. See, because the integral of the 1 over v squared is minus 1 over v, right? So then use fundamental thermal calculus. And so you can solve for, you solve this to solve this for 1 over VF is equal to 1 over V naught plus beta over M times x, the final x minus the initial x. And so there you go. The final velocity is, in fact, the reciprocal of the sum of the reciprocals, 1 over V naught plus beta over M. Well, that's not a reciprocal. There you go. I mean, I guess if I want, oh, I'm sorry, I forgot my problem. I was supposed to find V of x, right?
Yeah.
Fine, so I can do that. It's not a big. Sorry for the calculator. Let's see here. It lived a good life. V of x is just 1 over V naught plus beta over M times x minus x naught. So there you go. That would be V as a function of x, where I just happen to write it in terms of initial velocity and initial position as well. So anyway, hopefully these will help. There's a homework problem that's kind of sort of like these. I just wanted to include this. A little bit off the beaten track for us in terms of the math, but I did assign you a homework problem, so it seems mean to not talk about it at least a little bit. And also, I also like it as an example of this idea of integrating one side and the other with respect to different but corresponding bounds. It's a very useful calculational technique to derive specific formulas for applications. All right, with that, I want to talk a little bit about orthogonal trajectories in here. I've assigned you a problem or two about those. And it goes to a larger point of just building direct geometric data into differential equations. Like, let's just, let's play for a couple minutes. Let's come up with some differential equations which will have solutions with specific geometric features. For example, what if you wanted a differential equation? So here we're just going to do some thinking. So here, number one, let's say, what do you want? You want solutions where slope always 2. So what's the differential equation to express that? Starting out with a baby example. dy dx equal to what? Yeah, that's it. So that differential equation will automatically have slope 2 everywhere. This is kind of a silly example. You can integrate both sides. You get y equals 2x plus a constant, right? Not too exciting. What if you want solutions which are increasing for x greater than 2 and decreasing for x less than 2, right? Let me forget about x. Let's use y. I mean, there's lots of different possibilities, but here's one. You could do this. How about dy dx is equal to, let's see here, what is positive no, but it has to have a y dependence. How about this? I'll do another example. How about y minus 2? Try that expression, right? If y is larger than 2, that's positive, right? Which means that dy dx is what? Positive, so the function's increasing for such points. On the other hand, if y is less than 2, then y minus 2 is negative, and so dy dx is negative, so those functions are decreasing at such points. Can we solve this? Oh yeah, we can solve this. This is what? This is dy dx minus y is equal to minus 2, right? So this has an integrating factor of e to the x, actually. E to the minus x. So you see that's d dx of e to the minus xy is equal to minus 2 e to the minus x. Lo and behold, we get e to the minus xy is equal to plus 2 e to the minus x plus a constant. Solution, y of x equals to 2 plus c e to the minus x. I can even plot what those look like. What happens to these solutions? Whatever their aspirations are in life, eventually all of these go to 2. They all get sucked into y equals to 2 asymptotically. So here's some typical solutions. That's what they look like. As you can see, oh, I'm sorry, what did I do?
Would be c times e to the x.
Yes, it would. Yes. Whew, thank you. Oh, now my picture's wrong. Or you could do this. Fine. Try that again. Okay, so they all asymptotically go to 2, and they're blowing up, right? Oh. What? Oh. Hmm. What? No, it's definitely supposed to be a plus 2 because when I integrate e to the minus x, I get another minus 2 e to the x. Oh, anyway. It's fine. It's just it's not what I was thinking. I mean, they don't asymptotically go to 2 is the thing. I'm thinking of a different example. Sorry, guys. It will be the case that these functions are increasing when y is above 2, and they're decreasing when y is below 2, right? Oh, but the thing is, what was the thing about it? Is c is either what? There are 3 kinds of solutions here, right? That's what's blowing my mind, is I'm forgetting there's 3 different kinds of solutions, and that's what's messing with my thinking. Although, I guess that's just me, because you can't hear my thoughts, so thankfully, you're okay. Modulo the awkwardness of me thinking, of course. I'll try not to do that so much. All right, so y equals to 2 is kind of a stupid solution, right? This is a so-called equilibrium solution to this problem. dy dx equals to 0, right? That's a solution. Now, if c is greater than 0, what's the solution look like? C is greater than 0. It goes through 2 plus c at 0, right? And then it does this. It's always increasing because y is always greater than 2. On the other hand, if c is less than 0, this is 2 plus c. Like if c was equal to minus 1, it could be that. And then what does it do? That it's always decreasing, and y is always less than 2. So it does everything we said it should do. All right? ¿Es bueno? No. So you guys could think about other geometric traits you want in a solution set, and it's not hard to write down a differential equation which builds those, whatever your favorite facts are about derivatives, into the differential equation, and the solutions to that will be curves that fit the bill. So there's one kind of canonical example that we like to teach students because it's important to applications. For example, if these are the equipotentials, in other words, if these are the curves of constant voltage, in the theory of electrostatics, you learned that the electric field lines are perpendicular to these. Right? So if you want another family of curves, right, which is perpendicular everywhere to this family, it looks like what? In this case, they're just lines, lines through the origin, right? This would be, the green those are orthogonal trajectories to that family of circles. So an orthogonal trajectory to a given, given a family of curves, all right, if you can find another family of curves that whenever they meet the given family, they meet at right angles, this is said to be a family of orthogonal trajectories. So the lines and the circles form orthogonal trajectories. All right, make sense? So how would we derive that those are lines? I mean, of course, this problem is so geometrically simple, you can just see it from just common sense, right? Let me show you some uncommon sense. So what you want for orthogonal trajectories is if you have dy dx is equal to m, if that's given, then dy dx for the orthogonal trajectory is what? Minus 1 over m, right? This will give the orthogonal trajectories to, I need to give it a name, let me call it Pac-Man. So the orthogonal trajectories to the Pac-Man is, you just do minus 1 over the slope, whatever it is, right? So for my circle examples, we take our dy dx, which is what? Minus x over y, right? That's what's given. And we trade that for dy dx is equal to minus 1 over minus x over y. Because solutions to that differential equation will have minus the reciprocal of the slope of the original differential equation. It's really such a simple idea. And of course you can simplify this. This is what? Y over x, right? And then you do what? You got yourself dy over y is equal to dx over x. Integrate both sides. Natural log of the absolute value of y is equal to the natural log of the absolute value of x plus some constant. How do you solve that? How do you find an explicit solution there? Exponentiate both sides, right? So this gives me the absolute value of y is equal to e to the ln, the absolute value of x plus c, which is e to the c times e to the ln of the absolute value of x, which is e to the c times the absolute value of x. So if you'll allow me to continue this thought bubble over here, what we have then is we have the absolute value of y is equal to e to the c times the absolute value of x. Absolute values are fun though, right? Because you can get all the different cases by just putting down a what? Our favorite notation to get rid of absolute values here. So y is plus or minus e to the c times x, right? But you might as well just call e plus or minus e to the c what? M. And there you have it. That is the orthogonal trajectories to these circles. See how that works? So to find orthogonal trajectories, all we do is we take the given differential equation, form negative the reciprocal, right, and solve that. Assuming, of course, the differential equation is written as dy dx equals something, right? Any questions? No. I'll talk more about this again tomorrow, probably. I'm going to go on to the section 9.3 stuff now. I really should show you something, though, before I forget. Let me do that. So as you guys know, I have a website that I prepared for you guys. And I wrote notes for this course a few years ago. And I've posted PDFs of the chapters of those notes on the website, right? And one of those chapters is differential equations. So in that differential equations chapter, you'll find a presentation of this material, which is completely divorced from your textbook, right? Because we were using a different textbook when I wrote those notes. I think Stewart. But math is math, and these are still useful. So if you look at this, my chapter 16, and this is the course website, right? www.supermath.info, calculus 2, HTML. And you click on that, you'll find that you have tons of examples, which I will probably not cover in class because, well, I mean, there's too many examples to cover in a reasonable amount of class time in my silly notes. And I also have discussion about terms like general solution, implicit solution, the bigger picture of what differential equations are. But goodness gracious, just tons and 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 tons of examples. Oh, here's one. For example, For example, this example. Let's see here. I think I neglected to tell you that this is the logistic equation. I just presented it last time. I talked about what it meant, but I didn't tell you that it was a logistic equation. Oh, look, somebody left me a ruler. It's very full of the yucky dust. I think probably this ruler and then doing this is how this has gotten so yucky. You probably can't tell, but it's very smudgy. I have something else. Let's see here. I think I have something else. Oh, man. Haha. All right, so well, that's not really helpful. I always have this problem because I don't really want to lose this diffracting thing. There we go. So this is the logistic equation. Now we know how to solve it today, right? We just need to separate variables. And so I'll show you how that goes because it's kind of interesting. And this is also an example of, so like if you look at that, and this is the carrying, that was what I called C yesterday, but if you look at the logistic equation, you've got increasing for populations from 0 to the carrying capacity and decreasing for populations above the carrying capacity. And that's true independent of time. And if you look at the second derivative, if you differentiate the differential equation, you can find what the second derivative looks like. And if you do that, you come to this expression, and you can even derive, in terms of just the population alone, independent of time, right, the concavity of the solutions. kind of neat. And so the solutions look something like this. This is a graph of solutions. You got, if you have above the carrying capacity, they decrease. If you got below, they increase. There's these points of inflection at half the carrying capacity. It changes from concave down to concave up, other way around, concave down to concave up. And it's always concave, up here? Concave down, right? Now, how do you actually find those solutions? Well, that's what separation of variables does for you.
Actually, aren't the ones on top concave up? Says right here. Constantly increasing.
I'm sorry. You might be right. Oh, yeah, those are concave up. You're right. Yep. If we were to draw a secant line between any 2 points, it would be above the graph. So how do you actually solve that? Well, you separate variables, like so, and then you do partial fractions on this, right? Partial fractions, what's that? You guys already know that. It's like so Tuesday. So there's the partial fractions, and you do some algebra, and some more algebra, and some more algebra, and eventually you get to this. Population is a function of time, carrying capacity, and 1 plus some constant times e to the minus kt. As t goes to infinity, this drops to 0, and everything goes to the carrying capacity with the logistic equation. So there's that. All right. So I just wanted to remind you that this is here, and I even have what I'm about to talk about. In my notes, I talk about integrating factor second because, like I said, I'm just following the book. I did integration factor first for you guys. As you see, you could do one topic and then the other, or vice versa. Really, they're disconnected thoughts. And the next thought I have today is section 9.3, which is constant coefficient second order ODEs. In my notes, I refer to the differential equation as the bomb, and so I'm going to show you how to diffuse the bomb here, I guess, is one way to look at it. But anyway, I'm going to put it this way. I want to just remind you guys, this is there. You can look at it. There's tons of examples not in your book, which might be helpful to you. Now, if you can understand the material by just looking at the book, great. You don't have to look at my notes. It's fine. It's cool. It's up to you. So here we go. Section 9.3. Second order, constant coefficient ODEs. So basically, our goal, or mission if you choose to accept it, is to solve AY prime prime plus BY prime plus CY equals to 0 for A, B, C in the reals and A not equal to 0. Let me give this name star. So we want to solve this thing for any ABC that comes to us. All right. So the techniques that I've used up till now today have been relatively kind of step by step. I would say they're almost like derivations in the sense that I'm doing things I already know, right, step by step, and getting to the answer, pretty much, right? Like I always separate variables. Take the equation you're given, you separate the variables, you integrate both sides, you know? Or even the integrating factor technique. We take the thing we're given, we do something weird and find the integrating factor, but then you multiply and you take basically step by step modifying the equation you have to something you can integrate, right? So you haven't really left your comfort zone much there in some sense. The way we solve this is much more clever. We make a guess. Now, I can motivate that guess, but I won't, not to start with. To start with, I'm just going to make a guess, and I'm going to show you that it works. And then if we have time today, I'll give you more motivation. All right, so here's the guess. Without further ado, guess. Y equals e to the lambda x is solution to star for some lambda constant, some constant lambda. Sorry about my lambda. Most people write lambda like this. I write lambda like that. I would change it, but it's ingrained. I can't fix it at this point. Sorry about that. It has been complained my lambda looks like a 2. I'm sorry. Again, I will cite you to my previous comment. It's ingrained. I can't change it. You could say I have a writing disability when it comes to lambda. You have to respect that. Otherwise, you're bad people. Let's see here. So, I'm sorry to inconvenience you with my disability, but there it is. Oh no, this lecture seems to have taken a horrible turn. Let's see here. So what's dy dx? This y primes, by the way. We're assuming x is the independent variable, so like y prime is dy dx, right? Okay. So with that, what's y prime here? Right? What's y prime prime? Three? Did somebody say 3, or I just heard that? Sorry. So yeah, lambda squared e to the lambda x, right? So if my guess is right, if my educated guess is right, what do we need? So then we need what? A lambda squared y prime prime. Oh, sorry, y. Ah, idiot. Not you, me. E to the lambda x plus b lambda e to the lambda x plus c e to the lambda x equals to 0. This is required. This is what it means, right? For y equals to e to the lambda x to solve star, right? What is a solution to a differential equation? It means when we plug it in, it works, right? So if my educated guess e to lambda x is to work, when I plug it in, it has to solve this, right? Now, can you guys, so that's a necessary condition. Can you guys make that cleaner, easier to understand? Again, we can't fix the lambda problem. What's that? Group it. Kinda. What's that? Oh, you mean factor the e to lambda x out? Can anybody be greedier than that? How about we just take this equation and we divide by e to the lambda x? Can I do that without losing anything? Absolutely, right? Great. Yeah, e to the lambda x is always non-zero. I will agree to that. So a lambda squared plus b lambda plus c equals to 0. Now this is important. This has a name. This is the so-called characteristic equation of star. I can't spell characteristic equation for star. Apparently, if we can solve the characteristic equation, we can solve star. What is the characteristic equation? I mean, maybe if I wrote it like this, it would be better. I wouldn't do this usually, but ax squared plus bx plus c. Okay, so yeah. I mean, okay, we own this, right? I mean, this is... I wouldn't do that, though, because x has a different meaning here. That's why I use lambda. Let's look at an example.